In this exercise, we were asked to build a memoize decorator, a special decorator that would cache the result of a function call to avoid excess function invocations. It will be particularly appropriate for highly recursive functions or for functions that have very expensive operations. But before we got into the solution code, it's important to take a look at what the starter code is really doing. This is the template we have for a decorator. We define some new function that will be our decorator. And this decorator really is just a high-level transformation. It is itself a function that takes in a function and wraps it up into a new function it defines, which we've called a wrapper function, that accepts any number of arguments, a variadic collection of positional arguments and a variadic collection of keyword arguments, and then does something with those arguments and the captured function. Presumably, at some point, calling the function with your arguments that were captured. In this case, in our starter template, just passing those arguments along and returning the value back out. Finally, the decorator itself returns the wrapper that we've defined. So our solution code actually looks very similar, but just has a couple of different lines. To start with, we've attached a cache attribute to the function that we're capturing. This is going to be a dictionary associating snapshots of the arguments that are sent into the function with whatever the return value of the function ends up being. Now, inside of the wrapper function itself, we're doing some extra steps as well. First, we'll compute some hashable key from the arguments supplied to this function. We'll contain a tuple of the positionally supplied arguments, themselves a tuple, as well as a tuple that will make of the items the associations between the names and values of the keyword arguments supplied to this wrapper function. In some sense, this key is a pretty close approximation to a unique representation of the arguments that might pass into the function itself. Then we check to see if our key is already found in the function cache. This is the caching behavior, where if we have already found the key, then we're going to avoid doing some extra work. But if we have not found the key, we will first evaluate the function on the arguments that we've captured, and then save that in our cache at a value associated to the key of all of those arguments. Finally, after these two lines of code are executed, we will have associated at some function cache key the value of the function. So all we need to do is return that step itself. So this is hugely practical when you have code that is highly recursive, like a Fibonacci function. If we now take a look at the Fibonacci function that will use the memoize decorator, we'll see that this memoization makes much more complex calls computationally tractable. So if we look at these lines of code calling Fibonacci numbers for a variety of indices, we can actually run Python 3 fib.py, and it won't take forever. It will run even to the largest of our Fibonacci values relatively quickly, and that's making use of the caching behavior. We can ask Python to time, we can ask the operating system to time how long this takes, and we see that it takes just under 1/10 of a second. But if we were to remove this memoize decorator and ask for the Fibonacci values even just of the first two conditions here, without getting into the large cases, we'd find that it takes a little over 1/10 of a second to even get all the way up to 25. If we go a little larger and check, let's say 40 instead of just 25 or even 50 or 100, we can see that even here it's going to start to take quite a long time because these Fibonacci calls grow exponentially as you increase the index that you're looking at. So it could take quite a while to wait for this function to finish if you do not use the memoize decorator. And the cool thing about us having implemented this as a decorator means that we can use this @memoize decorator on any type of function we want to make a little faster by caching its results. Wow. Even just to count to the 40th Fibonacci number without memorization took 50 seconds, compared to our ability to get to the 100th one in 1/10 of a second using this cached decorator.